phenomenon in nature that defies everything we think we understand. Two particles can be separated by thousands of kilometers and still behave as if they were one. There is no cable, no signal traveling between them, and yet they react instantly, as if distance did not exist. Albert Einstein called it spooky action at a distance, unable to accept that such a thing could be real. But modern experiments have confirmed it time and time again. Today you're going to discover why quantum entanglement isn't just a laboratory mystery, but the key to technologies that will change the world, and perhaps our understanding of reality itself. By the way, if you like my video and subscribe, it's the most effective way to support me. If you also write where in the world you are watching from and what time it is, I love reading it in the comments. 1. Laboratories that entangled atoms miles apart. The achievement of entangling distant atoms is not limited to light photons. It has also been achieved with massive systems that allow stable internal states to be recorded. Schemes are used in which each atom emits a photon that travels through fibers to an intermediate node. There, a joint measurement is made, which, when it gives a specific result, collapses the whole into an entangled state, even though the atoms never touch. This method is called exchange entanglement and avoids transporting the atoms directly. The beauty of this method is that the photon acts as an ephemeral messenger and the atom as a long-lasting memory. Optical cavities and electromagnetic traps improve the efficiency of photon emission and collection, which would otherwise be easily lost. Clock synchronization and spectral filtering reduce fluctuations that would introduce random phases and destroy the correlation. However, performance remains low, requiring the process to be repeated many times until the desired event occurs. A crucial advantage is that, once created, entanglement can be stored in the atom for appreciable times. This allows consecutive nodes to be chained together and longer segments to be built without the correlation evaporating immediately. This gives rise to so-called quantum repeaters, devices that connect network fragments, renew entanglement, and correct errors. Without them, fiber attenuation would grow relentlessly with distance. This path opens a bridge between laboratories and real-world applications. Carrying entangled atoms over kilometers serves to test robust quantum communication protocols and to study the role of matter in preserving coherence. Each technical assembly that manages to keep the correlation alive is a lesson in how to tame a resource as powerful as it is fragile. 2. Records of particles entangled with satellites in orbit. Satellites offer a shortcut to bypass fiber losses, as the vacuum of space attenuates less than glass. By sending pairs of entangled photons from orbit to two separate ground stations, continental distances have been overcome at useful rates. The challenge lies in aiming with extreme precision, compensating for atmospheric turbulence, and maintaining the purity of the quantum state as it passes through the atmosphere. An orbital window of just a few minutes requires the protocol to be executed quickly. Large aperture telescopes, active tracking, and ultra-precise clocks are used to align ground records with the descending photon stream. Even when the number of pairs detected is small, it is enough to violate Bell's inequalities and demonstrate non-locality on geographical scales that until recently seemed unattainable. These links pave the way for hybrid networks that combine space segments and fiber segments. A satellite can act as a quantum key distributor between cities that do not share efficient ground infrastructure. The same hardware can test variations in teleportation and clock synchronization protocols with advantages over classical methods. The records are not just numbers, they are milestones in quantum engineering. Each increase in distance, rate, and fidelity translates into new security guarantees and confidence that the technology can scale. It is about moving from heroic experimentation to routine operation, where quantum technology ceases to be a laboratory trick and becomes the backbone of critical communications. 3. Entanglement and black holes in the same theoretical framework. One of the most intriguing conjectures states that the strong connection between quantum systems could be reflected as a geometric bridge in space-time. This intuition brings entanglement and black holes closer together, since the quantum information that seems lost when falling could be encoded in correlations that survive at the boundary of the system. Geometric language helps to visualize abstract relationships between states. The black hole information paradox becomes less puzzling if the apparent loss is explained by a redistribution of correlations. Instead of being annihilated, quantum information is repackaged into external degrees of freedom, maintaining a strict accounting of entropy. Entanglement acts as the currency that pays the bill for coherence. Simple models show that extremal surfaces, equivalent to mathematical bridges, quantify how much correlation connects two regions. Thus, the area of a boundary is not just geometry, it also measures how much information the parts share. Hence the intuition that gravity emerges as a collective effect of entanglement networks between underlying quantum blocks. This approach does not solve everything, but it offers a conceptual map where curvature ceases to be mysterious and becomes a ledger of correlations. The promise is to unify two worlds that seemed irreconcilable, one based on probabilities and the other on geometries. The meeting point would be entanglement as the fabric from which the shape of the universe emerges. 4. Global quantum internet as an entanglement network. A quantum internet does not replicate the current web. It complements it with capabilities that are impossible to falsify. Its fundamental building block is not the bit. It is the entangled pair that allows identities to be verified, inviolable keys to be distributed, and clocks to be synchronized with unprecedented margins. To achieve this, nodes that generate and store quantum states are chained together, while other nodes transport or renew them. The infrastructure includes quantum memories to store states without degradation, low-loss optical links, entanglement exchange mechanisms, and error correction protocols. Each link is subject to attacks from noise, attenuation, and phase drift, which is why purification cycles are designed to increase fidelity at the expense of sacrificing defective pairs. The balance between rate and quality is the art of these networks. Interoperability between different platforms is another challenge. Some memories work better with microwaves, others with visible light, and others with infrared. Quantum translators convert photons from one frequency to another without destroying coherence. This invisible engineering is what will allow a superconducting chip to communicate with a trapped atom or a diamond defect in another city. The utility goes beyond cryptography. A set of laboratories connected by entanglement can share reference states, compare measurements with extreme precision, and perform distributed tasks that would otherwise be inefficient. The quantum internet is a physically trusted network based on the laws of the microscopic world, not on classical mathematical promises. 5. Experiments that suggest effects before causes. Delayed choice setups and delayed decision entanglement, swapping test our temporal intuition. In these experiments, the choice of what to measure is decided when the particles have already been detected or when their trajectories appear to be closed. Even so, the resulting correlations match what would be obtained if the choice had been made earlier, which defies common sense. It is not a matter of sending messages back in time. It is that the theory assigns probabilities to the entire process as a complete block. Operational causality is preserved because no observer can exploit this effect to communicate faster than light. What changes is our narrative of how reality is assembled from scattered events. These tests are valuable because they force us to clarify what we mean by cause and effect in a world where measurement creates physical content. The measurement basis decision redefines which properties are relevant and which remain latent. The results remain consistent regardless of the order of certain operations, but without giving away shortcuts to violate relativity. The lesson is that time in quantum physics does not function like a tape that only moves forward uniformly. Some sequences can be rearranged without altering predictions, a freedom that is lost at the macroscopic level. Understanding these cracks in intuition opens the way for new protocol architectures and a less rigid philosophy of time. 6. Bell's test proven without loopholes. Early verifications of Bell's theorem suffered from technical gaps linked to imperfect detection and surreptitious communication between meters. Recent years have closed these loopholes with high-efficiency detectors and sufficient spatial separation to prevent local influences during the measurement window. Randomness generators based on independent physics choose the bases at the last moment. The result is a clear violation of inequalities that no model with local hidden variables can mimic. This victory is both conceptual and technological, confirming that the world is not composed of predefined properties waiting to be revealed. Measurement creates contexts, and those contexts cannot be replaced by a hidden script acting behind the scenes. Variants of the experiment use photons, electrons, ions, defects in solids, and hybrid combinations. Some use cosmic sources to decide measurement bases, reducing any suspicion of prearranged correlations. Others increase the distance between stations so that the light signals cannot influence each other during the recording window. Closing loopholes is not just an act of neatness. It allows violations to be used as certificates of randomness and as the foundation for security protocols independent of trust in hardware. Non-locality ceases to be a curiosity and becomes a tool with practical consequences. 7. The fragility of entanglement in the face of environmental noise. Entanglement is exquisite and therefore easily broken. Unwanted interactions with the environment introduce random phases and losses that turn pure states into mixtures. Decoherence acts like an eraser that smudges non-local correlations and returns systems to behavior compatible with classical intuitions. To combat this, error correction codes are designed to detect and correct alterations without directly measuring useful information. Entangled states are distributed across several qubits so that part of the noise can be identified and reversed. It is not a question of eliminating the environment, but of taming it so that its blows are not fatal. Materials engineering also plays a role. Cleaner substrates, interfaces with fewer defects, and magnetic shielding reduce leakage channels. Temperature is a constant enemy, forcing the use of cryogenics or the selection of platforms that operate at room temperature without sacrificing coherence. The design of electronic and optical controls prevents fluctuations that would cause phases to oscillate unpredictably. The message is twofold. The fragility of entanglement imposes limits, but it also guides us to improve techniques and understand which degrees of freedom are reliable. Every decibel gained against noise is a step toward longer networks and devices that use non-locality as an everyday resource. 8. Mischius, and the record for entangled photons in space. A dedicated satellite showed that it is possible to distribute pairs of entangled photons to stations separated by thousands of kilometers. The platform stabilizes its orientation with precision, generates pairs through nonlinear processes, and compensates for beam dilution with large aperture telescopes on the ground. The orbital visibility window is used to accumulate enough coincidences in a short time. In addition to non-locality tests, encrypted communication protocols were implemented where any attempt at espionage is revealed by the deterioration of correlations. The satellite also participated in the teleportation of ground-prepared states to an orbital receiver, demonstrating that the fundamental building blocks of a quantum network can operate outside the atmosphere. One of the least talked about achievements is the management of synchronization between distant clocks so that detections correlate with nanosecond precision. Without that synchronicity, the pairs would disappear among millions of random clicks. The experiments validate that systems engineering is as important as basic physics. The impact goes beyond the record. The mission tested technologies that will scale up to constellations dedicated to quantum services. What is now a demonstration will become infrastructure, with relays ensuring global coverage and redundant links, providing robustness against weather and failures. 9. Entanglement in diamond defects at room temperature. Nitrogen vacancy centers in diamond host electrons, whose spin is manipulated and read with light and microwaves. Surprisingly, this platform remains coherent at room temperature, avoiding cryogenics and simplifying the hardware. Two separate defects can be coupled by photons that escape from the crystal and combine in an interferometer. The diamond acts as a rigid cage that protects the spin from vibrations and electrical fluctuations. The purity of the crystal and its proximity to the surface determine how much noise reaches the system. Dynamic decoupling techniques cancel out slow perturbations and extend the time during which the spins maintain well-defined phases. The entanglement between two centers allows these defects to be used as quantum memories in network nodes. It also enables magnetic sensors that exceed classical limits by cooperatively correlating multiple spins. The light emitted by these centers serves as a natural interface with optical channels for information transport. The ability to operate without extreme temperatures opens the door to compact devices and deployments outside the laboratory. A future with urban quantum repeaters could be based on this platform, combined with other systems that provide higher photon rates or better integration with photonic circuits. 10. Quantum teleportation demonstrated in laboratories and optical links. Teleportation does not transfer matter. It transfers the quantum state from one system to another at a distance. It works when two nodes share an entangled pair, and the sender performs a joint measurement between its local particle and the state it wishes to send. The result of that measurement, communicated by a classical channel, indicates what transformation to apply at the receiver to recreate the original state. There's no shortcut for the classical channel, and therefore no communication faster than light. The magic lies in the fact that the state recreated at the destination never traveled as an intermediate copy. Non-cloning prevents the original and the copy from existing at the same time, so that the act of measuring at the source destroys the local state while enabling its appearance at the destination. Teleportation has been demonstrated with photons in fiber and through free space, with ions in traps, and with defects in solids. In all cases, fidelity depends on the quality of the shared entanglement and the accuracy of the joint measurement. It is a key component for quantum networks, as it allows quantum information to be moved between memories without the need to physically move the carriers. Beyond communication, teleportation is used to assemble logical blocks in distributed computing and to inject fragile states into inaccessible areas of a processor. It becomes a quantum-level routing tool, redesigning how information flows in complex architectures. 11. Quantum correlation versus classical correlation. Two classical variables can be correlated if they share a common cause or history. These correlations never violate well-defined limits that express intuitions about realism and locality. Entanglement breaks down these barriers and produces patterns of coincidences that no classical mechanism can mimic without allowing secret communication or implausible conspiracies. The profound difference is that in quantum mechanics, there are no pre-existing values waiting to be revealed. Properties emerge in the act of measurement and do so in tandem, such that choices on one side condition statistics on the other. This dependency does not enable useful messages, but it does negate explanations based on hidden catalogs. Another unique feature is the monogamy of entanglement. If a system A is highly entangled with B, its ability to become entangled with C is limited. This restriction is a natural security feature, facilitating the design of protocols where a potential spy is excluded by correlation geometry rather than external conventions. Understanding the separation between classical and quantum correlation helps to avoid misunderstandings when talking about synchronicities or intuitions. Quantum physics offers amazing phenomena, but with precise rules. It is this precision that turns surprise into reliable technology. 12. Sensors that exceed limits thanks to entanglement. When measuring small phase or field variations, quantum noise imposes limits that scale with the number of resources used. Entangled states and squeezed light can improve this scaling and achieve sensitivities that exceed the so-called standard limit. Interferometers with correlated inputs record subtle imbalances that would otherwise remain hidden. This principle has already translated into real improvements, for example, by introducing squeezed light into gravitational wave detectors. Noise reduction in a quadrature allows weaker signals to be seen without saturating sensors. The technique requires careful balancing, as improving one variable worsens the conjugate one, and we do not want to squander any advantage. On smaller scales, quantum sensors based on diamond defects measure magnetic fields in neurons or materials with unprecedented spatial resolution. By correlating multiple centers, noise is averaged cooperatively, yielding a gain that was not accessible with independent elements. Calibration and classical noise rejection remain crucial. The promise is to transform measurement in disciplines ranging from geodesy to biology. It is not just a matter of lower numbers on a sheet of paper. It is the possibility of observing phenomena that were below the threshold and that change theories when they finally become visible. 13. Attempts to entangle biological systems. A controversial frontier explores whether living structures can sustain observable quantum coherence. Proposals involving bacteria coupled to optical cavities and levitated nanodiamonds suggest ways to transfer entanglement from photons to mechanical degrees of freedom belonging to more complex objects. Controls are delicate because any vibration destroys the correlation. Although there is no definitive consensus, there are indications of coherence in biophysical processes, such as energy transfer in photosynthesis. There, excitonic states, appear to explore parallel paths for short periods of time before stabilizing. This is not proof of living entanglement in the strict sense, but it does show that nature can take advantage of quantum resources under the right conditions. The interest is not mystical, but metrological and technological. If biological systems could be entangled in a reproducible way, sensors and proof-of-concept tests would emerge to study cellular processes with an unprecedented level of control. It would also test the extent to which decoherence imposes a boundary between the living and the inert in operational terms. In the meantime, caution is required. It is necessary to separate speculation from evidence, reproduce results, and isolate genuine quantum phenomena from classical artifacts. The value of this approach lies in proposing clean experiments where quantum mechanics is expressed unambiguously in increasingly larger systems. 14. Entanglement and the arrow of time. In closed systems, quantum dynamics are reversible, yet we experience irreversibility, which we associate with increased entropy. Entanglement helps reconcile both ideas, since as it grows between subsystems, information is distributed in such a way that recovering initial states becomes impractical, though not impossible. The arrow of time emerges from this dispersion. Simple models show how a small set mixes with a large environment and loses identifiable features. What we call heating can be described as entanglement that expands its reach and erases fine coincidences. Irreversibility is effective because reconstructing the global phase with astronomical precision is beyond our reach. This framework illuminates phenomena such as quantum thermalization, where subsystems reach stable distributions without the need for classical collisions. It also explains why certain error correction operations require resources that grow rapidly with the size of the system. The cost of maintaining quantum order increases with the natural tendency to mix. Thinking about time from this perspective suggests that arrows are not set in stone. They are emergent properties of how parts are connected. The promise is to unite thermodynamics, information, and quantum dynamics into a single narrative that explains why the past seems fixed and the future open. 15. Echoes of the Big Bang as a source of cosmic entanglement. Quantum fluctuations of primordial fields were stretched during early expansion and left traces in the structures we see today. These traces include angular correlations in background radiation and subtle patterns in the distribution of galaxies. Initial entanglement may have marked a preference for certain combinations of modes. Analyzing these correlations is complex, because the universe has evolved and pure states are not conserved. Even so, non-trivial statistical signatures can reveal a shared quantum origin. We look for deviations from Gaussianity and alignments that cannot be explained by subsequent local processes. Each clue connects cosmology with quantum field physics. If entanglement played a role, then large-scale space-time inherited information from tiny scales. This suggests that understanding the current distribution of matter and radiation is equivalent to reading a compressed file from the earliest stage. Reading it requires separating out late astrophysical effects that mask the message. The reward would be monumental. Validating that cosmic structures bear the imprint of primordial non-local correlations would finally unite the largest and the smallest in the same narrative. The history of the universe would be understood not only as expansion and cooling, but also as the unfolding of a pattern of entangled information that still resonates. 16. Clues to quantum gravity through entanglement. One of the greatest challenges in physics is to unite quantum mechanics with general relativity. Entanglement appears to be a fundamental clue because it behaves like an invisible thread connecting regions of space-time. Studies in conformal field theories show that the amount of entanglement in a system is related to areas of geometric surfaces, something surprisingly similar to the way gravity describes horizons. This coincidence has inspired the holographic principle and conjectures such as ER equals sign EPR, which suggest that Einstein-Rosen bridges may be nothing more than geometric expressions of correlated quantum states. This relationship implies that gravity, far from being an independent field, could emerge from a tapestry of quantum correlations. In other words, the curvature of space-time would be a secondary property of how the fundamental states of the universe are organized. This challenges classical intuition, where geometry seemed the most basic thing. If gravity is deduced from quantum information, then understanding entanglement is understanding the very essence of reality. Experiments are still far from proving this, but simulations in condensed matter systems offer accessible scenarios. There, entanglement is measured with tomography techniques and can be connected to gravitational analogs. These tabletop experiments allow us to test conjectures and generate insights into how a complete theory of quantum gravity could be constructed from information principles. The appeal of this line of research is twofold. On the one hand, it unites two pillars of physics that seemed irreconcilable. On the other, it offers a common language, that of quantum information, which extends to both the cosmos and the laboratory. Every time we measure entanglement with precision, we are, perhaps without knowing it, touching the very fabric of gravity. 17. Trapped ions showing controlled entanglement. Ions trapped in electromagnetic fields are one of the most advanced systems for studying entanglement. In ultra-high vacuum chambers, charged particles are suspended and manipulated with laser pulses. These pulses induce collective couplings that generate quantum correlations between the spins of each ion. The advantage is that there is almost total control over position, electronic state, and collective vibrations, allowing states to be created and measured with unprecedented precision. Ion entanglement is not just an academic experiment. It forms the basis of quantum computing architectures where each ion is a qubit. By correlating them, logical operations can be performed that go beyond what classical computing can handle. This makes ion traps a testing ground where fundamental physics and applied technology come together. Researchers are able to maintain coherence for relatively long periods of time thanks to cryogenics, isolation, and exquisite electromagnetic control. However, the challenge lies in scaling up to hundreds or thousands of ions without losing fidelity. Despite these limitations, demonstrations of quantum gates and simple algorithms already confirm the power of the approach. This system represents the best of both worlds. On the one hand, it reveals fundamental phenomena such as collective entanglement, dynamics, and correlation growth. On the other, it shows a realistic path toward useful quantum machines. Each new record with trapped ions is both an experimental breakthrough and a glimpse into the computing of the future. 18. Atomic clocks improved by entangled states. Atomic clocks depend on the regularity with which specific atoms oscillate between energy levels. The precision limit is known as the quantum standard limit and is governed by independent statistics. But introducing entanglement between atoms creates a collective state that reduces uncertainty and allows for more accurate readings. These states, called spin-squeezed, squeeze the error distribution in one direction to free up sensitivity in another. This technique opens the door to clocks that not only mark seconds more accurately, but redefine what we understand by synchronization. Imagine navigation systems that do not rely on vulnerable satellites, but on distributed autonomous clocks. Imagine also geodetic measurements capable of detecting tiny changes in the Earth's gravitational field, useful for predicting earthquakes or studying natural resources. The technical challenge lies in creating and maintaining these entangled states in large groups of atoms. Noise, collisions, and environmental fluctuations tend to destroy the delicate correlation. However, sophisticated optical and microwave techniques have achieved significant improvements that already surpass conventional clocks in certain laboratory scenarios. Beyond practical applications, these advances show that entanglement is not just an exotic curiosity, but a measurable resource that can be incorporated into concrete instruments. Every more stable second is a reminder that quantum physics, when applied well, can redefine our basic tools of civilization. 19. Superconductors that protect quantum coherence. Superconducting materials offer a unique environment for maintaining stable quantum states. When resistance disappears and electrons pair up in Cooper pairs, collective states emerge that are best described as macroscopic quantum waves. These waves are ideal for sustaining qubits, circuits that can enter into superposition and become entangled with others. The appeal of superconductors lies in their integration with existing electronic technology. Chips manufactured using conventional techniques are adapted to contain quantum circuits, accelerating the development of quantum processors. Correlations between superconducting qubits are manipulated with microwave pulses and magnetic fields, offering fast and flexible control. The central problem is the fragility of these states in the face of material defects and electromagnetic fluctuations. Every small error can destroy coherence and with it, entanglement. That is why so much is being invested in improving the purity of materials, in shielding, and in error correction algorithms that counteract fragility. Even so, progress has been remarkable. Quantum machines with dozens of superconducting qubits already show collective dynamics that are impossible to simulate with classical supercomputers. Entanglement thus becomes the silent engine of a new technological era that is rapidly advancing toward maturity. 20. Decoherence that destroys entanglement and how to avoid it. Decoherence is the silent enemy of quantum physics. It occurs when a quantum system interacts with its environment and loses the ability to maintain coherent phases. Entanglement, which is delicate by definition, is particularly vulnerable. A single uncontrolled interaction can scatter the information and turn the state into an incoherent mixture. To avoid this, environments that are as isolated as possible are designed, but absolute isolation is impossible. That is why active techniques such as dynamic decoupling have been developed, which applies pulse sequences to cancel out unwanted interactions. Other strategies include encoding information in subspaces that are naturally immune to certain types of noise. Quantum error correction is another essential front. By distributing information across multiple qubits, it is possible to detect and correct errors without directly observing the content. This approach, inspired by classical information theory, is adapted to quantum nature with ingenious mathematical constructions. The challenge is enormous, but also productive. Every time decoherence imposes a limit, physicists invent a new technique to push that limit a little further. Thus, entanglement survives longer and becomes a useful resource, not just a theoretical curiosity. 21. experiments in Vienna that changed the consensus. Vienna has become an epicenter for testing non-locality. There, research groups conducted experiments with entangled photons that closed crucial gaps in Bell's tests. Technical rigor, sophisticated detectors, and innovation in photon sources positioned the city as a benchmark in the experimental validation of quantum mechanics. One of the milestones was the transmission of entangled pairs through kilometers of fiber in real city conditions. These experiments demonstrated that quantum communication is not limited to laboratory environments, but can be adapted to existing infrastructure. By integrating quantum sources into urban networks, the feasibility of future everyday applications was proven. The international community watched closely as each Viennese experiment closed the door on alternative explanations based on local hidden variables. The more sophisticated the tests became, the clearer it became that entanglement was not an experimental artifact, but an inherent property of the world. The legacy is twofold. Vienna not only provided solid experimental data, but also trained generations of researchers who are now taking these ideas around the world. In every university and every laboratory that explores quantum communication today, the echoes of those pioneering experiments can be heard. 22. Bell's inequalities and their real physical meaning. Bell's inequalities are mathematical expressions that define what can be expected from any theory based on local and realistic variables. When violations appear in experiments, those theories are ruled out. The fascinating thing is that this is not a technical subtlety, but a paradigm shift in how we understand reality. The result implies that we cannot simultaneously hold the idea that properties exist before they are measured, and that influences are limited to propagating at the speed of light. Something has to give. Quantum mechanics sacrifices local realism and forces us to accept a world where measurement actively participates in the creation of results. These inequalities serve not only as philosophical proof, they also function as practical tools for certifying that a system is effectively entangled. They are used in quantum cryptography protocols to verify security without relying on the hardware provider. It is a clear example of how an abstract concept becomes a useful tool. The deeper meaning remains a matter of debate. Some interpret entanglement as pointing to an underlying non-local reality, others as simply reflecting limits in our language. In any case, Bell's inequalities have earned a place as one of the most revolutionary intellectual achievements of the 20th century. 23. Retrocausality as a viable interpretation. Some physicists propose that entanglement can be interpreted as a sign that the future influences the past. This retrocausality, although puzzling, fits into certain mathematical frameworks and preserves the temporal symmetry of quantum equations. From this perspective, what happens in a detector depends not only on previous events, but also on decisions made afterwards. This does not imply that we can send messages to the past, because statistics always respect observable causality, but it suggests that the arrow of time we perceive could be an emergent illusion. Entanglement would be a clue that nature does not distinguish between before and after as much as we assume. Delayed choice experiments have fueled these interpretations by showing that results remain consistent even when decisions are made after the particle has passed through the apparatus. The retrocausal reading is a way to reconcile the paradox without resorting to undetectable hidden variables. Retrocausality remains controversial, but it fuels philosophical and physical debates alike. Whether or not it is the correct explanation, it forces us to recognize that time in quantum physics is a much more flexible concept than we thought. 24. Twin photons traveling as coordinated shadows. When a nonlinear crystal receives an intense laser, it can split a photon into two lower-energy photons, called twins. These photons are born entangled and show correlations in polarization, momentum, and arrival time. When separated, they continue to act as if they share a common destiny. This is the method most commonly used in laboratories to generate entanglement. The beauty of this process is that, even though the photons travel along different paths, measuring one instantly reveals information about the other. Experiments use optical fibers, mirrors, and beam splitters to guide each photon to different detectors where the correlation is confirmed. It is a ballet of light choreographed by quantum laws. These sources are so versatile that they have been used in almost all experiments involving non-locality, teleportation, and quantum cryptography. Their efficiency and relative technical simplicity allow results to be reproduced in multiple laboratories around the world, consolidating entanglement as a reproducible phenomenon rather than an isolated oddity. Every time two twin photons behave like shadows of the same being, our intuition is shaken. They remind us that quantum reality does not conform to everyday logic, but follows its own rules that we are still learning to decipher. 25. Entanglement in crystalline solids manufactured in clean rooms. Not everything happens in isolated atoms or light particles. Engineers have learned to generate entanglement in solid crystals, where controlled defects act as qubits. By exciting and reading these defects with optical pulses, robust quantum correlations can be induced in materials manufactured with nanometric precision. The advantage of solids is that they integrate thousands of devices on a single chip, which is essential for scaling technologies. In addition, they allow classical and quantum electronics to be combined in compact platforms, opening the door to hybrid devices with applications in communication and computing. The challenge is to control the heterogeneity of each crystal. Small impurities, internal stresses, or unforeseen defects can introduce noise that destroys coherence. That is why extreme purification techniques, cryogenics, and advanced lithography are used. Each improvement in manufacturing translates into stronger and more durable entanglement. This field exemplifies how quantum physics is no longer just a matter for fundamental physics laboratories and is now fully entering the field of materials engineering. The future of entangled solids will be both scientific and industrial. 26. The prohibition on cloning quantum states. One of the most counterintuitive rules of quantum physics is that an unknown state cannot be copied. This prohibition, called the no-cloning theorem, ensures that teleportation does not produce duplicates, only transfers. Entanglement is directly related to this limitation because it is the resource that allows states to be moved without breaking the rule. This has profound implications. It means that quantum information is more fragile, but also more secure. No one can make a perfect copy of your qubit to spy on you without leaving a trace. The security of quantum cryptography relies on this fact, which does not depend on technology, but on the very structure of nature. Non-cloning explains why quantum communication requires additional classical channels. You cannot simply send a copy of the particle. You need to use entanglement as a vehicle. Thus, limitations become strategic resources. In a world where digital copying is trivial, quantum non-cloning forces us to rethink how we value information. What cannot be duplicated without being altered takes on an almost physical character, as if it were an unrepeatable substance. 27. Fiber optic links crossing cities and mountains. The existing telecommunications infrastructure has become a large-scale laboratory for quantum physics. Using commercial fiber optics, entangled pairs have been transmitted over tens and hundreds of kilometers. This allowed quantum cryptography protocols to be tested under real conditions, with classical data traffic sharing the same cable. The challenge is attenuation, which increases with distance and limits the coincidence rate. To overcome this, quantum repeaters are deployed to regenerate entanglement at intermediate nodes. Each node combines memories, photons, and purification protocols to extend the network without losing fidelity. These experiments have crossed tunnels, bridges, and mountains, proving that quantum technology can survive in hostile environments. They've also shown how quantum networks can be integrated with classical systems, a necessary condition for their real-world deployment. Each extended link confirms that the vision of a quantum internet is not science fiction, but an engineering project in progress. Entanglement leaves its mark on every kilometer conquered. 28. Quantum vacuum that stirs invisible correlations. The quantum vacuum is not an inert nothingness. It is a sea of fluctuations that spring up and die out in a very short time, leaving subtle statistical traces that can be measured with experimental ingenuity. Among these traces are correlations that cannot be explained by a classical image of space as a passive stage, but rather by fields that vibrate even in their lowest energy state and share information on a microscopic scale. Our intuition changes completely. What we call a vacuum is a fabric that beats with entangled modes that rarely manifest themselves directly, but influence observable forces and spectra. A concrete clue emerges when we restrict the field with well-defined geometries and polished surfaces. The vacuum pressure changes and a measurable force appears, revealing that the modes allowed are not the same inside and outside the cavity. This difference is best understood as a rearrangement of field correlations, which, when confined, alter the energy balance and produce thrusts that have no classical analog. The lesson is compelling. Modifying the environment modifies the vacuum, and with it the correlations that sustain seemingly independent phenomena. Another revealing scenario comes with accelerated detectors or observers subjected to intense gravity. What one calls a vacuum, the other perceives as real particles and effective heat. This observer dependence suggests that vacuum correlations are not mathematical accessories, but operational entities that participate in energy transfer and measurement limits, with consequences that connect information, thermodynamics, and space curvature. The idea of a universal vacuum is replaced by a family of operational vacuums linked to motion and the gravitational field. Exploring this territory is not a theoretical whim. It holds technological and metrological promises, ranging from ultra-sensitive sensors to materials designed to manipulate vacuum modes with nanometric structures. Every time we control a cavity or a guide that filters frequencies, we are also touching the background correlation pattern, and that control opens up avenues for amplifying weak signals or reducing fundamental noise in precision instruments. 29. Quantum cryptography that detects any spy. Key distribution protocols based on individual photons make entanglement and non-cloning direct allies against intrusion. If someone intercepts and measures, they inevitably alter the statistics and are exposed by an increase in errors that they cannot hide. This security does not depend on an algorithm being indecipherable. It depends on nature, preventing unknown states from being copied without leaving a trace, which renders many classic assumptions about brute force and future computing obsolete. Trust is transferred from mathematical promises to a physical certificate embedded in the structure of the microscopic world. The next step is to not even trust the devices themselves. Tests based on Bell violations allow us to certify that the device produces genuine non-local correlations and therefore secure keys, even if the manufacturer is an adversary. This idea of device-independent security changes the governance of critical networks because it reduces the need for endless audits and shifts verification to the domain of coincidences that no classical simulation can reproduce. A statistical spike in the right place is worth more than 100 compliance stamps. Real links must coexist with attenuation, losses, and phase fluctuations, giving rise to operational strategies such as decoy states and continuous error rate estimation that measure channel health in real time. When fidelity falls below calculated thresholds, the protocol is interrupted and no key is delivered, a preventive denial that is as valuable as success because it prevents a weak session from becoming a leak. This discipline of cutting off in time is the difference between physical security and perceived security. As these techniques migrate to urban fibers and space links, an ecosystem emerges with quantum repeaters, memories, and frequency converters that point to a network with layers of security that do not depend on guarded secrets, but on verified correlations. The promise is not just to encrypt better, but to build infrastructures that reveal intrusion by physical principle and cannot be silently degraded by a patient attacker. By the way, if you like my video and subscribe to it, that's the most effective way to support me. 30. Natural phenomena that use quantum coherence. Biology has learned to work on the edge of noise, where some processes seem to take advantage of coherence and perhaps entanglement during brief windows that are sufficient to gain efficiency. Energy transfer in photosynthetic complexes shows spectroscopic signatures compatible with superpositions that explore parallel paths before settling on the most favorable destination, a trick that reduces losses and accelerates the flow of excitation in temperate environments. It's not magic, it's evolutionary engineering that tolerates disorder while preserving temporal clarity when convenient. Another clue has been discussed in avian magnetoreception, where light-generated radical pairs would have dynamics sensitive to weak magnetic fields. In this scheme, quantum correlations between spins would affect chemical reactions that biology would have exploited for orientation. The evidence continues to be refined, but the simple fact that there are plausible routes for weak signals to be amplified thanks to internal coherences already forces us to rethink what is possible in hot and humid environments. The quantum frontier no longer coincides with absolute zero. Quantum mechanisms have also been proposed in smell and certain enzymatic processes, hypotheses that are driving new ultrafast and microscopy techniques that seek unambiguous signatures of functional coherence. Even when entanglement is not the protagonist, transient coherence can improve efficiency and selectivity, which in turn inspires bio-inspired material designs and energy transport pathways in artificial devices. Nature serves as a test bed, not an isolated anecdote. The learning curve for technology is immediate. If complex processes retain useful coherence under intense noise, then there are protection and recapture strategies that can be translated into integrated photonics, catalysis, and molecular electronics. The practical limit is no longer temperature, but rather a design that knows when to let things vibrate and when to freeze phases so that the result is favorable. 31. Quantum teleportation with emerging biomedical applications. Quantum teleportation does not transfer bodies or tissue. It transfers states of information that accurately describe how a microscopic system behaves. This nuance opens up a little-discussed biomedical avenue that combines quantum sensors and memory banks, where fragile states are prepared in one place and faithfully recreated in another. Imagine photonic probes that extract quantum signatures from molecules or cellular nanoenvironments, and instead of sending them as imperfect copies, reconstitute them exactly in a remote laboratory for analysis without degradation. The fidelity of this operation depends on shared entanglement and a joint measurement that consumes the original while enabling its rebirth at the destination. The practical benefit arises when samples are scarce or extremely sensitive to the environment. A vibrational or electronic state taken from a protein can be lost in milliseconds if transported classically. But if its quantum description is teleported, the receiving laboratory can subject it to precise spectroscopy without exposing the patient's tissue to more light or heat. This logic would also allow identical states to be compared in different devices and equipment to be calibrated with references that cannot be cloned by design, increasing metrological traceability in biomedicine. The bottleneck lies in generating useful entanglement between nodes at realistic rates and in operating quantum memories compatible with humid or hot environments. Engineering must translate cryogenic components into robust, encapsulated, and sterilizable devices, something that is currently only glimpsed in prototypes. Even so, the path forward is clear, because the same building blocks already work in fiber optic links and photonic chips, and biology needs exactly what quantum technology promises to offer without copying or alteration. When this chain is closed, biomedicine will gain a completely new layer of diagnosis and control. Quantum states prepared in situ in an operating room could be teleported to reference laboratories for immediate characterization, and finely tuned photodynamic treatments will respond to measurements that could never be made if we were limited to classical instruments. 32. Aspects experiment that settled historical doubts. For decades, it was suspected that violations of Bell's inequalities concealed technical flaws. Alain Aspect's series of experiments clearly demonstrated that there was no trickery involved and that quantum correlations exceeded any reasonable classical limits. The key was to alternate the orientations of the analyzers during the flight of the photons, closing the possibility that the particles carried a fixed instruction. That operational maneuver was a slap in the face to intuition, because it forced us to accept that measurement decisions on one side affected the statistics on the other, without an explanatory local mechanism. The legacy of those tests goes beyond the numbers. They established standards of experimental honesty, where every possible escape route is identified and closed with faster hardware, more sensitive detectors, and stricter synchronization. This culture of closing loopholes became a model for later generations, who would extend distances, improve rates, and take non-locality from the optical table to city networks. The philosophical dimension translated into technological tools. Once the world accepted that quantum correlations were real and certifiable, device-independent cryptography emerged, relying not on manufacturer promises, but on Bell's violation itself. These protocols are a direct consequence of the spirit that animated Aspect's tests, where nature certifies the honesty of the experiment better than any human audit. Looking back, we can see how an idea discussed on blackboards ended up changing communications engineering and our understanding of reality. Aspect's experiment not only closed an open discussion, it ushered in an era in which entanglement is a measurable and exploitable resource. not merely a source of perplexity. 33. The space-time that can emerge from entanglement. One school of thought suggests that the geometry we perceive as space and time emerges from patterns of quantum information. In this view, distance is not a primary property. It is a reflection of how much information two regions share. When entanglement is abundant, the zones feel close. When it is reduced, the metric stretches. The formulas that connect area and entanglement entropy point to a microscopic accounting that, when aggregated, gives rise to a curved macroscope. This perspective reorders priorities. Instead of quantizing the given geometry, networks of quantum degrees of freedom are constructed whose entanglement will then reproduce an effective space. Toy models show how simple correlation maps can generate surfaces with coherent geometric properties. If these models capture something of real physics, gravity ceases to be an independent force and comes to be read as the elasticity of an informational fabric. The appeal of this idea is that it unifies terms that were previously studied separately. Quantum computing concepts, such as complexity and purification, become effective gravitational variables. Conversely, geometric intuitions help organize and visualize networks of qubits, offering heuristics for designing more robust codes and architectures. The promise is not yet fulfilled, but the bridge is already being crossed in both directions. Whatever the definitive theory may be, everything points to entanglement not being a mere embellishment, but rather the very fabric that sustains the shape of the world. 34. Information that is not lost in black holes. The old intuition was that everything that falls into a black hole is erased forever, including information. Quantum physics, however, does not allow for the destruction of information, and that tension gave rise to one of the most debated paradoxes. The emerging consensus is that information does not disappear. It is encoded in a highly non-local way in the correlations between the whole and its radiation. Entanglement acts as a strict accountant that balances inputs and outputs, even when the process appears to be thermal. The arguments are based on entropy balances and models where small information leaks accumulate until unitarity is restored. The intuitive image is that of a book being leafed through, scattering letters across the horizon in a seemingly random order, but which together hold a message that can be recovered with immense resources. This is not an operational consolation for astronauts, but it is a conceptual relief for a physics that does not want to give up its internal coherence. The key tool is once again entanglement. If radiation is emitted without correlation with the interior, entropy grows in a manner incompatible with the conservation of information. If, on the other hand, there is finely distributed correlation, the balance sheet balances and the whole story remains unitary. Surfaces that maximize effective areas provide clues as to where to account for these hidden connections. The profound message is that the conservation of information is not an abstract whim. It is the thread that sews together quantum mechanics and gravity, and its tension is resolved when we give entanglement the leading role in the accounting of the extreme universe. 35. The holographic image of the universe driven by entanglement. The holographic principle proposes that the description of a volume can be encoded on a surface of lower dimension. That bold statement makes sense when we observe that entanglement entropy in quantum systems follows laws of area, not volume. Surfaces are then not mere geometric boundaries. They are hard drives that store the accounting of what happens inside. This idea has concrete translations into models, where a theory without gravity at the edge captures phenomena with gravity inside. In that dictionary, quantities of information and thermodynamic magnitudes are related to the curvature and dynamics of space-time. Entanglement at the edge is equivalent to geometric bridges that cross the volume, suggesting that sewing or cutting correlations literally changes the shape of the interior. If this intuition is correct, manipulating information patterns could, in principle, deform effective spaces in quantum simulators. It's not about curving your living room, but using qubit architectures to explore gravitational phenomena in controlled environments, where measurement and adjustment are possible without telescopes. The laboratory would become an information planetarium. The conceptual value is formidable. Holography gives coherence to scattered observations about entropy, horizons, and entanglement, and offers a compass for navigating the territory between quantum theory and relativity. Again, the common thread is quantum correlation as a measure and driver of geometry. 36. Superconducting qubits entangled on chips. Superconducting circuits converted into qubits dominate the experimental scene today because of their scalability and the speed at which they operate. The entanglement between these qubits is created with microwave couplings that move energies in a controlled manner and allow logic gates in nanoseconds. In that brief instant, the states combine into collective superpositions that no classical transistor can mimic. The engineering that makes this possible is a symphony of ultra-clean materials, precise lithography, and control electronics that generate millimeter-scale pulses. Every imperfection translates into decoherence and loss of fidelity, so the entire chain must maintain a purity that borders on the impossible. In return, the system offers integration with proven manufacturing techniques and a path to thousands of qubits on a single substrate. Entanglement on this platform is not a conceptual luxury. It is the fuel for algorithms that promise to accelerate specific tasks, such as quantum chemistry, simulation, or optimization. Without correlations, there is no advantage, which is why teams devote much of their effort to measuring, stabilizing, and recycling entangled states as a calculation progresses. The trend is toward increasingly modular machines, where small quantum processors are connected with photonic links and share resources. There, entanglement becomes a high-fidelity bus that connects scattered physical blocks and turns a set of chips into a single extended computer. 37. Shared superposition between coupled systems. When two systems are subtly coupled, they can enter into a shared superposition in which neither party possesses properties defined on its own. The image of two dancers joined by a cloth is useful because pulling on one end redefines the pose of the other without transmitting a classical command. This collective superposition is the step prior to deep entanglement and is observed in ions, photons, and defects in solids. The interest lies in the fact that these superpositions are not just mathematical abstractions. They produce measurable effects by interfering with trajectories and amplifying sensitivities. A sensor based on shared superposition reacts cooperatively and registers changes that would go unnoticed with isolated elements. Similarly, a communication protocol can perform maneuvers that no classical channel would accept without excessive noise. Operating in this regime requires exquisite control of phases and couplings. Small drifts ruin the harmony and return each part to its independence. That is why stable optical references, frequency filtering cavities, and calibration routines that finally adjust the coupling parameters every few seconds are used. The intellectual dividend is that these superpositions teach us how entanglement is born and what conditions feed it. At the frontier between the coupled and the truly non-local, most of the useful quantum technology we will see in the next decade is being cooked up. 38. Universal simulation based on entangled networks. Simulating other quantum systems with controllable platforms is one of the most tangible promises of the field. Networks of entangled qubits can emulate exotic materials, chemical reactions, and dynamics that overwhelm classical supercomputers. The advantage lies not in raw power but in affinity, because the computer and the problem share the same language of amplitudes and phases. For the simulation to be universal, a gate base capable of approximating any desired evolution is needed. Entanglement is the tool that connects local blocks and builds effective interactions that replicate the target system. With sufficient resources, this approximation achieves arbitrary fidelities and allows the exploration of intricate energy landscapes where minima and barriers govern collective behaviors. The practical utility is seen in catalysis, drug design, and new materials. Calculations that browse configurations impossible to enumerate with classical bits become accessible when the dynamics of the qubits themselves traverse the relevant state space. Each improvement in coherence times and gate rates translates into real problems that change status from unapproachable to approachable. The horizon is close cooperation between physicists, chemists, and engineers who map industrial challenges to quantum circuits and return solutions that are validated in the laboratory. In that loop, entanglement is more than a curiosity. It is the clay with which simulations that we could only imagine before are molded. 39. Wigner's paradox and his friend with entanglement. The well-known story of Wigner's friend adds a human observer inside the laboratory who performs a measurement, while Wigner, from outside, treats the whole as a superposition. The entanglement between the measured system and the internal observer strains the notion of unique facts, because what is a definitive result for one may be a coherence for the other. This scenario points out that the boundaries between system, apparatus, and observer are not trivial. Experiments with photons and small processors have implemented versions of this paradox, showing that two incompatible descriptions can coexist without operational contradiction. In each case, the entanglement between the system and the recorder means that erasing or retrieving information changes what can be said about the process without prohibited communication appearing. The practical lesson is that talking about facts in quantum requires specifying the frame of reference and access to information. What seems like a distant philosophy impacts how we design protocols and what assumptions we take for granted when certifying security or composing computing subroutines. Rather than resolving the paradox, these essays teach us to formulate questions with greater precision. Entanglement appears as a moderator that allows for operational agreements without requiring a single narrative about what is real in all frameworks. 40. Demonstrations on the International Space Station. Bringing quantum experiments into low Earth orbit eliminates much of the loss that plagues fiber links and provides a laboratory with microgravity and long nights. In this environment, the distribution of entangled pairs between modules and ground stations tests network architectures that will be the backbone of global services. With compact telescopes and stabilized platforms, the International Space Station becomes a test bed where engineering and physics shake hands. The operational challenge includes vibrations, radiation, and thermal cycles that force each component to be hardened. Photon sources, detectors, and control electronics must survive conditions that no terrestrial laboratory could replicate for months. This adversity acts as a natural filter, because only truly robust solutions pass the test, and are ready to migrate to dedicated constellations. In addition to links, microgravity allows for the study of cold atom interferometry with long trajectories, where entanglement amplifies sensitivity to subtle accelerations. These measurements are not an academic whim. They improve navigation, geodesy, and resource prospecting from heights where coverage is unmatched. The strategic value is clear. Whoever masters space quantum networks will master standards of synchronization, security, and global coordination. The station is the springboard for that infrastructure, and entanglement is the common language that its nodes will speak. 41. No signaling, despite apparent instantaneity. The fact that quantum correlations appear instantaneously does not mean that we can send superluminal messages. The distributions of individual results remain random on each side, and only when comparing lists is the joint pattern revealed. This detail preserves observable causality and makes entanglement compatible with special relativity. The temptation to imagine a hidden signal is strong, but it clashes with the impossibility of controlling the result of a local measurement. You can choose what to measure, not what result you will obtain. Therefore, any attempt to encode bits in those choices fails when it comes to reconstructing them at the other end without an auxiliary classical channel. Paradoxically, this limitation is a virtue for security. Protocols distribute keys, knowing that no spy can influence results remotely or copy states without being detected. Non-signaling is a seal of physical integrity that does not depend on the honesty of manufacturers or industrial secrets. Accepting this point clears up misunderstandings and focuses attention on what can be done. Quantum networks do not violate relativistic limits. They use them as foundations. Physics establishes boundaries and offers very specific advantages within them. 42. Uncertainty that fuels the power of entanglement. The uncertainty relationship is not an unfortunate obstacle. It is a resource that, when well managed, allows noise to be redistributed and useful correlations to be created. By squeezing fluctuations in one variable and accepting more noise in its conjugate, systems achieve levels of precision that would be impossible if each part acted alone. This engineering of randomness is the soul of compressed states and sensors that break standard limits. Entanglement organizes this uncertainty collectively. It is not a matter of reducing the total noise, but of weaving it so that it has less effect on the magnitude that matters. In an interferometer, for example, light inputs are prepared, whose fluctuations are partially cancelled out at the output, revealing weak signals that were previously buried. Operating in this regime requires constant calibration and models that quantify exactly where the benefit lies and where penalties appear. The trade-off between sensitivity and robustness is a delicate dance that only pays off if the environment is mastered and technical noise channels are closed. That is why every dB of improvement is celebrated as a hard-won achievement. The end result is that uncertainty ceases to be the enemy and becomes raw material. Quantum physics does not promise absolute control. It promises intelligent control over disorder, and entanglement is the loom with which that disorder is ordered in our favor. 43. Parallel universes as an interpretation of non-locality. There are interpretations that read entanglement as evidence of multiple branches where results coexist in realities that do not interfere, except in subtle statistical patterns. In this interpretation, correlations do not require distant influences because each branch contains a coherent outcome, and global coincidence emerges when we compare stories. This is not a direct empirical statement. It is a way of giving consistency to equations without hidden local variables. This view has the virtue of avoiding mysterious collapses at the cost of multiplying worlds. For many, this is a high price to pay, but it offers a clean ledger where unitarity is never broken and information always flows reversibly. Entanglement would then be a sign that two branches share history before diverging. The fertility of this reading lies not in proving other worlds, but in inspiring algorithms and protocols that treat information as a resource that is distributed among complementary descriptions. Tools for interference and partial reversal are best designed if we think that what is not seen is not lost, but only resides in components that we are not reading. Beyond personal preference, these interpretations require precision when discussing facts and probabilities. Entanglement works the same under different interpretations, but each one illuminates different strategies for taking advantage of it or explaining its paradoxes. 44. New philosophical metaphors born from these effects. Entanglement has renewed a philosophical vocabulary that had been concerned with substance, cause, and subject for centuries. Now we speak of primary relationality, where what exists in the first place are the connections and not the carriers. Two systems are not given and then related. They are defined in part by their relationship. This conceptual reversal has implications for epistemology and ethics because it forces us to think of knowledge and action as cooperative phenomena. In this key, the boundaries between self and world are interpreted as operational boundaries rather than ontological barriers. Physics says nothing about values, but it suggests that sharp divisions are useful approximations, not ultimate truths. Entanglement reminds us that separation is often a convenient fiction and that reality appears entangled from the outset. These metaphors do not replace equations, but they guide questions and avoid old pitfalls. Talking about intrinsic properties without specifying measurement contexts leads to confusion. Talking about relationships as foundations avoids this trap and better aligns language with data. The result is a more honest dialogue between science and philosophy, where the former provides hard constraints, and the latter offers frameworks for thinking about the consequences. Curiosity and promise coexist here without hyperbole, with the sobriety demanded by a phenomenon as counterintuitive as it is fruitful. 45. Advanced metrology with sensitivity beyond noise. Metrology is the art of measurement, and its current frontier involves quantum strategies. By intertwining multiple resources, from photons to cold atoms, rules of operation are constructed that squeeze information out of areas where classical noise dominates. Long baselines, high-quality cavities, and Bayesian estimation algorithms combine to transform invisible signals into reliable data. The benefits have already been seen in gravitational wave detectors, optical clocks, and magnetometers with microscopic resolution. In each case, entanglement reorganizes error statistics so that what matters is cleaned up and what is irrelevant is tolerated. The cost is a delicate design that demands long-term stability and personnel who understand both hardware and information theory. These advances are not a luxury exclusive to large laboratories. As sources and detectors are miniaturized, industrial and medical possibilities emerge. More stable submarine cables, finer subsoil mapping, less invasive diagnostics, and navigation with less dependence on external signals are examples where the quantum advantage translates into resilience and efficiency. The operational lesson is that better measurement changes what is possible across the entire knowledge value chain. Entanglement allows us to see further and more clearly, and each improvement in sensitivity alters questions that were not even asked before because we lacked the instruments to attempt to answer them. 46. Coordinated measurements, 1,200 kilometers apart. Distributing entangled pairs across continental distances and taking nearly simultaneous measurements has been a litmus test for non-locality because it eliminates the possibility of subliminal influences during the observation window. The key lies in stabilized clocks, optical paths that minimize turbulence, and algorithms that match timestamps with nanosecond precision to distinguish real coincidence from background noise. Distance is no longer an absolute enemy. It is a design parameter that can be tamed with optics and synchronization. These experiments use stations that choose measurement bases at the last minute, sometimes with celestial sources feeding randomness generators to rule out suspicions of prior conspiracies. When correlations violate classical limits on this scale, there is no longer any room for discrete local explanations that rely on hidden messages. There is no place for tricks that travel thousands of kilometers undetected. The practical value is that these demonstrations validate network architectures that aim to cover countries and continents with quantum services. If the correlations survive the elements, then the foundations of the quantum internet do not depend on shielded laboratories. The engineering that makes the signal stable over such long distances becomes a field manual for real-world deployments that must coexist with weather, vibration, and shared infrastructure. Physics clears up doubts, and engineering picks up the gauntlet. Each increase in distance and fidelity strengthens the notion that non-locality is an operational resource and not a curiosity. Statistics cease to be philosophy and become a service contract that offers security and synchrony with guarantees that no classical technique can match without additional hypotheses. 47. Hidden programming versus quantum randomness. The tension between hidden variables and intrinsic randomness has guided decades of experimental design. If particles followed a fixed script, coincidences would have to respect limits that Bell tests repeatedly break. To close any loopholes, some experiments have used light from quasars or distant stars to decide measurement bases, pushing back in time any possible collusion between source and detectors. The conclusion is increasingly solid. The quantum world does not fit a narrative of pre-recorded instructions. Accepting genuine randomness does not mean resigning oneself to chaos. It means working with distributions that cannot be reduced to local causes, but follow laws with overwhelming precision. This randomness can be certified and harvested to create numbers that even the equipment manufacturer could not predict, an advantage that carries over to cryptography and simulation. The philosophical surprise becomes a gold mine of utility. Pedagogy matters. It is easy to confuse randomness with ignorance, but in this context, we are talking about limits of knowledge that cannot be reduced by more data or better sensors. Measurement does not reveal a pre-existing property. It brings it into the world in a framework that defines which questions make sense to ask. The script is not written, but the rules are clear. The balance is counterintuitive and fruitful. The absence of hidden programming that explains local coincidences opens the door to technologies that certify hardware impartiality and build trust in phenomena that do not allow for classic cheating, a type of honesty that can be audited with accounts rather than promises. 48. Entanglement observed in large molecules. Bringing superposition and quantum correlations to increasingly massive systems is an exercise that challenges preconceptions and improves techniques. Interference with fullerenes and macromolecules has shown that complex objects retain coherence when isolated and cooled sufficiently. The next step is to transfer entanglement to internal degrees or mechanical modes, a goal that already has optomechanical prototypes and traps that levitate nanoparticles and make them dance to the rhythm of light. The boundary between micro and macro shifts with each new result. The difficulty is not conceptual, it is engineering. Every vibration, every collision with residual gas, and every thermal fluctuation steals phase and destroys the delicate synchrony that makes it possible to observe non-classical patterns. Ultra-high vacuum chambers, temperature controls, and optical filters become surgical tools with which to carve the environment until it is compatible with extended coherence. There are no shortcuts, only room for patient improvement. Demonstrating entanglement in large molecules is not a sporting record. It is a test of how much we can protect and manipulate complex systems without decoherence returning them to average behavior. If that protection scales, chemical sensors with unprecedented sensitivity and new windows for studying reactivity and transport in soft materials will appear. The science of life and function gains a new microscope. Even if entanglement is maintained for only short periods of time, the simple fact of creating and reading it in objects with thousands of atoms redefines what we consider achievable. The notion that quantum dies as size loses strength when the technique perseveres and proves otherwise. 49. Reality seen as a pattern of intertwined information. One way of interpreting modern physics is to understand matter and fields as accounting for information. In this interpretation, intertwining is not unusual. It is the building block that defines what is close to what and what can influence what. The structure of correlations determines the effective topology, and what we call particles are excitations of a fabric that is organized according to rules of symmetry and information. The mental map changes, substance gives way to relationship. This perspective is not just a metaphor. The spectrum of entropy and other measures of correlation is used to identify phases of matter that are not distinguished by local order, but by how degrees of freedom are entangled over long distances. Materials with conductive edges and insulating interiors are better understood when looking at their information pattern than when insisting on traditional parameters. Many-body theory thus gains new and powerful tools. Furthermore, this view unifies domains that used to run parallel. Quantum computing, emergent gravity, and condensed matter now share metrics and concepts, allowing insights and techniques to be transferred with unusual fluidity. An improvement in error-correcting codes can inspire a diagnosis in holography, and a geometric lemma can suggest a more robust architecture for qubits. Compartmentalization is broken down. The result is a common language that does not require sacrificing precision. On the contrary, it forces us to quantify relationships that were previously described with general words, and that quantification raises detailed questions that push both theory and experiment toward verifiable predictions. 50. Entropy and entanglement as two sides of the same coin. Entropy measures disorder in thermodynamics and measures lack of information in information theory. In quantum systems, these notions come together when entanglement grows and distributes information between parts that can no longer be described independently. A subsystem may appear hot, even though the whole system is in a pure state, simply because its partner retains phase that it no longer controls. The apparent warmth is a record of lost correlations. This framework clarifies why processes that are unitary at the global level become irreversible at the local level. Recovering the initial state would require coordinating degrees of freedom that have already dispersed throughout the system. The arrow of time appears as a statistical tendency to distribute correlations rather than concentrate them, and that tendency is measured with entropies that grow predictably, except in carefully orchestrated twists. Thermodynamics becomes a practical information theory. When these ideas are applied to black holes and strongly correlated systems, an entropy curve appears that first rises and then falls as information is recovered in correlated outputs, a picture that has guided the debate about whether physics retains the memory of what happens to it. This is not a detail. It is a consistency test for any complete theory. Understanding this duality allows us to design protocols that exploit the growth of entanglement to generate certified randomness or to hide information in such a way that only specific cooperations can untangle it. An organic cryptography that does not depend on a single lock, but on many hands at once. 51. Intertwining in hot environments with precise engineering. It is commonly said that quantum dies with heat. But platforms such as diamond defects, quantum dots, or mechanical resonators show that coherence can survive and be used if noise is compensated for with active control and appropriate material designs. The key is to identify which degrees of freedom are less sensitive and how to decouple them from vibrations and stray fields without completely isolating them. The frontier is no longer a fixed temperature. It is a noise budget that is managed. Techniques such as concatenated pulses, magnetic shielding, and architectures with protective symmetries allow entangled states to maintain fidelity during useful operating windows even without cryogenics. Temperature is no longer a barrier, but becomes just another variable that is compensated for with redundancy and correctable error. Operating at room temperature enables portable applications and urban deployments. These advances have a direct impact on sensors and network nodes because they reduce costs and sizes, accelerating the transition from tabletop prototypes to field equipment and integrable devices. They also invite exploration of non-traditional materials with favorable noise environments that were previously ignored because they were not extreme. Platform diversity becomes a strategic advantage. With each high-temperature demonstration, confidence grows that useful quantum computing does not require perfect laboratory conditions, but rather techniques that can negotiate with reality as it is, with heat, vibration, and variability that are tamed with design and control software. I want to make a quick reminder. If you want to support me, you can click on the Join button at the bottom of the screen. Your support is very valuable to me. Thank you in advance. Let's continue with our video. 52. Distributed computing with entangled resources. A single quantum processor encounters physical and engineering limits, so the natural alternative is to connect several modules with links that share high-fidelity, entangled states, thus performing tasks that no isolated node could complete. The idea is reminiscent of cloud computing, but here the central resource is not classic bandwidth. It is the availability of correlations that enable quantum data teleportation and non-local gates. The machine map becomes a network. Orchestration depends on quantum memories that store states while the rest of the protocol arrives, and on entanglement swaps that extend the range without losing fidelity. Each jump adds noise, so purification cycles are programmed that sacrifice defective pairs to raise the quality of those that follow. A trade-off between rate and precision that is resolved according to the task. The quantum compiler learns to speak network. The dividend is twofold. The logical size of the processor is expanded and resilience is gained because a local failure does not sink the calculation if quantum routing reconfigures alternative paths. This resilience is reminiscent of Internet protocols, but with new physical rules that impose different limits and opportunities. Network topology becomes a critical performance parameter. As these architectures mature, complex chemistry simulations, optimization, and quantum learning can be distributed among specialized nodes, each with a powerful platform, all connected by the thread of entanglement that acts as an operations channel and not just a passive messenger. 53. Quantum entanglement in macroscopic objects. Coupling light with tiny mirrors or stretched membranes allows macroscopic mechanical modes to enter correlated states, a feat that requires taming thermal vibrations and overcoming the fear of working with masses visible to the naked eye. When the movement of a mirror correlates with the optical field in a non-classical way, unmistakable signs appear that the boundary between micro and macro is negotiable with good engineering. Classical mechanics gives way. These experiments open doors to extremely sensitive force and displacement sensors because two entangled oscillators can respond cooperatively to disturbances that would otherwise be below the noise level. They also serve to study whether there are decoherence mechanisms that grow with size and do not appear in small systems, a question that is both philosophical and operational. Scale becomes an experimental variable. Creating and reading these correlations requires high-quality cavities, lasers with ultra-low phase noise, and feedback cooling techniques that remove energy from mechanical modes without touching them with classical fingers. The margin for maneuver is narrow, but the benefit is enormous because every decibel of improvement in coherence equates to more sensitive channels for measuring forces, masses, and times. Mechanical metrology becomes quantum. The underlying message is clear. There is no wall prohibiting entanglement in large systems. There is a technical slope that is scaled with patience and increasingly refined tools, opening up a domain where macroscopic intuition conforms to the evidence and not the other way around. 54. Quantum tunnels and their link to non-locality. The tunnel effect allows a particle to appear on the other side of a barrier without crossing it in the classical manner, a rarity that is measured in currents, chemical reactions, and electronic devices with atomic thicknesses. Although it does not imply superluminal signals or violations of relativity, it does suggest that the probability amplitude is distributed non-locally, and that the notion of a single trajectory loses its operational meaning. Classical intuition stumbles and learns. Tunneling time has been the subject of intense debate, with indirect measurements and internal clocks attempting to define how long the process lasts without introducing artifacts that confuse the phenomenon with the measurement. What emerges is an image where the question of how long it takes lacks a single answer because different definitions capture different aspects of a dynamic that does not resemble a step-by-step journey. Physics invites us to refine our language. In solid-state quantum devices, tunneling becomes a resource. Qubits are coupled and uncoupled thanks to barriers that are adjusted with voltages and allow information to be transferred without excessive losses, while effective non-locality facilitates joint operations in short times. Entire architectures are designed around how much and how passage is allowed. Barrier control is logic control. Understanding this link between tunneling and practical non-locality helps avoid misunderstandings about signals faster than light, while exploiting real advantages in operating speed and sensitivity, a combination that turns old paradoxes into everyday engineering tools. 55. Signs of entanglement in string theories. Models that connect theories without gravity to curved spaces with gravity have revealed that measures of information on the quantum side translate into areas and distances on the geometric side, a sign that entanglement plays a leading role in the construction of effective space. Relationships between complexity, entropy, and volume offer maps where calculating an informational quantity becomes equivalent to calculating a surface within the emerging space. Mathematics supports intuition. These correspondences allow us to study black holes, plasmas, and exotic phases with tools that were previously separated by disciplinary walls. A difficult calculation on one side becomes more accessible on the other, and vice versa, fueling predictions that can then inspire tests on materials or in controlled quantum simulators. The circulation of ideas accelerates. A striking consequence is that cutting entanglement in quantum theory is equivalent to cutting bridges in geometry, suggesting that informational operations are reflected as surgeries of space, a powerful image for thinking about how connectivity changes without moving matter. Topology becomes dynamic through information. Geometric intuition gains a new dictionary. It is not about using strings to answer all questions. It is about using the dictionary to explore deep relationships between correlation and form. A program that has already yielded conceptual fruits and promises to guide new tabletop experiments that mimic geometries with qubit networks. 56. New quantum materials designed with entanglement. The classification of topological phases showed that not all order is visible in a local parameter. Some phases are differentiated by how their degrees of freedom are entangled at a great distance, a property that is captured by entropy spectra and non-local linkage functions. This understanding allows the design of materials where edges conduct without dispersion, while the interior remains insulating, a combination that reduces losses and suggests applications in metrology and robust electronics. Information guides chemistry. Quantum simulations and many-body calculations spend hours measuring entanglement indicators that anticipate transitions and exotic properties, saving time and blind trials in the laboratory. Instead of groping around, informational signatures are sought that predict useful behaviors before synthesizing the compound. Exploration becomes more surgical. In addition, internal entanglement control promises more stable qubits that are protected by symmetries and phase geometries, a path complementary to active error correction. If protection comes from the factory, operating costs fall and scale increases. The logical architecture relies on materials with embedded informational memory. With each material tested, it is confirmed that information-driven design is not a fad, but a path to increased performance, stability, and functionality, where entanglement is not suffered but used as a rule and a compass. 57. Quantum measurement as a theater of paradoxes. The act of measuring is not a formality. It is an interaction that creates facts and can erase them if designed subtly. Quantum erasure experiments show that information about a particle's path can be removed afterwards and restore interference that seemed lost without allowing for impossible signals. The scenario challenges a simple linear narrative and forces us to describe complete processes rather than isolated snapshots. Operational causality is maintained. Intuition is adjusted. Contextuality adds another layer. The result of measuring one property may depend on what other properties are measured alongside it, a feature that has no classical equivalent and has been verified with ingenious experimental designs. In this theater, the apparatus and its configuration are part of the system, not neutral spectators. The boundary shifts according to the script. These paradoxes are not embellishments. They are guides for building communication and computing protocols, where what is measured and when it is measured changes what is possible to do with the available states. An algorithm can benefit from keeping options open until the last step, just as a plot gains tension when the outcome is decided at the end. The literary comparison is useful and limited. Physics rules. As these ideas are integrated into metrology and networks, quantum measurement ceases to be a problem to be hidden and becomes a tool to be choreographed, with which practical advantage is achieved without violating basic limits, a maturity that distinguishes the field as it moves from perplexity to engineering. 58. Entanglement as the strategic resource of the century. Throughout human history, certain resources have defined eras: iron, gunpowder, oil, electricity. Today, quantum entanglement is beginning to be considered by many as the modern equivalent, an intangible resource, but one so decisive that it can determine which countries or corporations dominate the next technological era. Its value lies in the fact that it cannot be manufactured using conventional methods. It can only be generated and preserved under controlled conditions, where quantum physics dictates the rules. This rarity makes each entangled pair a currency of high strategic value. Governments already see entanglement as an element of sovereignty. Secure quantum networks, independent navigation systems, and military sensors beyond the reach of conventional technology depend on it. Investing in laboratories, satellites, and personnel training is a silent global race, as intense as the space race of the mid-20th century. The difference is that here it is not about getting to a place, but about mastering a principle that changes the very nature of information. Corporations are also getting involved because quantum cryptography is the shield for financial, medical, and strategic data. The first company to successfully integrate accessible quantum services on a large scale will have an almost unbeatable advantage in security and trust. We are not talking about academic curiosity. We are talking about billion-dollar contracts and infrastructure that will sustain digital life for decades to come. Entanglement is, therefore, a resource that transcends basic science and becomes a geopolitical and economic issue. What was once a paradox is now capital. Mastering it does not mean understanding it in a book. It means deploying it in practice and making it the backbone of a new technological order. 59. Cosmic non-locality on a large scale. So far, we have tested non-locality in laboratories and satellites, but the natural question is whether the cosmos itself exhibits patterns of quantum correlation on a large scale. If the universe was born from a compact, entangled state, traces of that connection could be recorded in cosmic background radiation or in the distribution of galaxies. Searching for non-locality on astronomical scales involves combining cosmology, particle physics, and information theory, a multidisciplinary challenge that is beginning to take shape. One clue lies in long-range correlations that cannot be explained by local classical processes, such as anomalous alignments in microwave radiation maps. Although there is no consensus, some researchers speculate that these structures could be echoes of primordial correlations that survived billions of years. The entire universe would, in a sense, be a slow-motion Bell experiment. The implications are overwhelming. It would mean that what we see in telescopes is not just matter organized by gravity, but a living pattern of correlations that cross cosmic boundaries. Reality would cease to be a mosaic of independent regions and become a continuous tapestry where the pieces share invisible information. If confirmed, cosmic non-locality would completely change the way we conceive of space. The intergalactic void would not be absolute silence, but a channel of correlations connecting what we believed to be unconnected. Cosmology would suddenly become a branch of information theory. 60. From the laboratory to everyday life, thanks to entanglement. The first entanglement experiments were complex, delicate, and so fragile that it seemed impossible to imagine applications outside specialized laboratories. However, in just a few years, the technology has gone from optical tables full of mirrors to compact chips that fit in the palm of your hand. This miniaturization means that we will soon see everyday devices based on entanglement without the need for advanced physics knowledge. The most obvious examples are secure communications and ultra-precise clocks. But the list does not end there. We can envision navigation systems that do not rely on GPS, medical diagnostics that work with minimal samples, and environmental sensors capable of detecting pollutants at levels impossible for conventional equipment. The promise is to transform security, health, and industry with a resource that until recently was considered a mere philosophical paradox. The transition is happening because engineering has learned to tame noise and produce robust entanglement. Every improvement in materials, optical control, and correction algorithms brings the phenomenon closer to the real world. The value chain is no longer in one-off experiments, but in reproducibility, cost, and scalability. The result will be a future where the word quantum will no longer sound exotic and will become commonplace. Just as today, no one is surprised that a cell phone uses satellites and relativity to locate you. Tomorrow, no one will be surprised that your data is protected by invisible entangled pairs traveling around you. 61. Hybrid networks combining land and space. The limitation of optical fibers to transport entanglement over long distances is compensated for by space links. But what will be truly revolutionary is combining both worlds in hybrid networks. Imagine a satellite distributing pairs between cities and terrestrial fibers, connecting intermediate nodes, creating a network that covers entire regions with redundancy. It is not a question of replacing, but of weaving layers that reinforce fidelity and coverage. The challenge is technical, translating between different wavelengths, synchronizing clocks on multiple platforms, and managing losses at interfaces where space and land meet. Each step is a challenge of precision, because a single misalignment can destroy the quantum state. But each step achieved brings the vision closer to reality and brings the quantum network closer to a planetary scale. The advantage is obvious. A hybrid network is more robust and more difficult to disrupt. If one segment fails, the other can take over. In addition, space offers communication windows over oceans and regions without terrestrial infrastructure, while fiber offers stability in dense urban environments. The combination is synergistic, not competitive. When these networks are rolled out, the notion of a global quantum internet will cease to be a promise and become infrastructure. Entanglement will know no geographical boundaries, traveling across land and sky as a fluid resource that ensures communications and planetary synchronization. 62. The relationship between entanglement and computational complexity. A fascinating mystery is how entanglement relates to the complexity of a calculation. The more entanglement grows in a system, the more difficult it becomes to simulate it with classical computers. In a sense, the degree of entanglement measures how deep a problem is and how impossible it is to mimic with conventional resources. Complexity ceases to be an abstract number and becomes a physical property. This relationship provides a practical compass. Researchers can measure indicators of entanglement in an algorithm to estimate whether it is worth trying to simulate it or whether only a quantum processor can handle it. Thus, entanglement is not only a resource, it is a metric of the boundary between the possible and the impossible. The connection also raises philosophical questions. If complexity grows with entanglement, could the universe limit the number of accessible correlations as a way to regulate the available information? Some suggest that complexity could be a physical principle as fundamental as energy or entropy, and that entanglement would be its natural fuel. In any case, the lesson is clear. Computational complexity is not just dry mathematics. It is engraved in the structure of reality, and entanglement is the mirror in which that complexity becomes visible, tangible, and measurable. 63. Quantum correlations in brain biology. For years, it was thought that the brain was too warm and chaotic to sustain useful quantum correlations. But recent studies have suggested that certain neural structures, such as microtubules, could maintain quantum coherence for longer than expected. Although the experimental evidence is still preliminary, the mere possibility of functional entanglement in brain processes arouses enormous interest, because it would imply that the mind operates not only with electricity and chemistry, but also with quantum information. The debate is heated. Some argue that the time and temperature scales of the brain annihilate any coherence before it can influence cognitive processes. Others argue that evolution could have taken advantage of niches where noise becomes a resource rather than an enemy, as in photosynthesis. If the brain manages to maintain correlations at a deep level, we may have to rewrite how we understand consciousness, memory, and even creativity. Experiments attempting to address this issue range from measuring ultra-weak magnetic fields to simulating neural dynamics in controlled quantum systems. None has provided a definitive answer, but all agree that the boundary between the biological and the quantum is more blurred than was thought decades ago. The brain could be a natural laboratory of collective correlations, more sophisticated than we ever imagined. The promise is immense. If brain biology employs entanglement in some way, it would not only explain abilities that seem mysterious today, but also open the door to technologies inspired by the very workings of the human mind. Quantum neuroscience could be the next great revolution. 64. Entanglement as a driver of artificial photosynthesis. Natural photosynthesis has shown signs of using quantum coherence to transfer energy with great efficiency. Inspired by this, engineers are seeking to replicate the phenomenon in artificial systems that capture sunlight and convert it into chemical energy with much higher efficiency than conventional panels. In these designs, entanglement would act as an invisible catalyst that directs energy toward optimal paths without excessive losses. This approach is not science fiction. Prototypes of synthetic molecular complexes that exhibit coherent transfer patterns already exist. By designing materials that protect and channel quantum states for just the right amount of time, researchers hope to exceed the efficiency ceiling of classic solar cells. The trick is to maintain the delicate balance between control and freedom, allowing energy to explore paths without dispersing into thermal noise. The energy implications are enormous. Artificial quantum photosynthesis could revolutionize clean fuel production, allowing solar energy to be stored in stable chemical bonds with unprecedented efficiency. That would mean abandoning dependence on fossil fuels and taking a radical leap forward in sustainability. Entanglement, in this case, is not a conceptual luxury. It is the secret ingredient that nature has been using for millions of years. Copying that secret and translating it into technology could be the key to solving one of the greatest problems of our civilization. 65. Experiments with synthetic diamonds for telecommunications. Laboratory-grown diamonds with controlled defects, such as nitrogen vacancy centers, have proven to be outstanding platforms for storing and manipulating quantum states. Unlike extremely fragile systems that require cryogenic temperatures, these defects can operate even at room temperature, making them ideal candidates for urban quantum telecommunications. The entanglement generated in these structures can be transferred to photons traveling through optical fibers, making it possible to use them in real networks. One of the advantages of synthetic diamonds is their durability and stability, attributes that set them apart from other more delicate platforms. Their integration into photonic chips opens up the possibility of compact repeater stations that could be placed in data centers, telecommunication towers, or even portable devices. In this way, entanglement ceases to be a laboratory resource and becomes practical infrastructure. Current experiments focus on extending coherence time and improving the rate of photons emitted without sacrificing quality. As these problems are solved, the path to a diamond-based quantum internet becomes clearer. The promise is a robust and flexible network where security is guaranteed by the fundamental laws of physics. In perspective, synthetic diamonds are the best example of how a luxurious and aesthetic material is transformed into a strategic tool for the communication of the future. What was once a jewel becomes a technological pillar. 66. The role of entanglement in dark matter. Dark matter constitutes most of the mass in the universe, yet it does not interact directly with light. Some theories speculate that its behavior could be explained not only by unknown particles, but also by large-scale quantum correlation patterns. Entanglement, in this context, becomes an intriguing candidate for explaining how invisible structures maintain cosmic coherence. The most daring hypothesis suggests that dark matter could be a collective state of entangled fields that do not manifest themselves in a classical way. In this framework, gravity would not be the only thread linking galaxies, but also a tapestry of quantum correlations that do not interact with photons but affect global dynamics. Although still speculation, it opens doors to astrophysical experiments seeking indirect traces of such correlations. Underground dark matter detectors, gravitational lensing maps, and cosmic simulations could offer clues to this hidden entanglement. Any statistical deviation in distributions or unusual correlations on cosmic scales would be pure gold for theorists. The challenge is to separate these traces from more conventional effects. If any role for entanglement in dark matter were confirmed, we would not only have a partial explanation for one of the greatest enigmas in cosmology, but also a demonstration that quantum correlations can extend to literally universal scales. 67. Optical micro-resonators that generate the entangled pairs. In modern laboratories, small optical rings made from silicon or silicon nitride chips have proven to be efficient sources of entangled photons. These micro-resonators take advantage of nonlinear processes that convert a pump photon into two correlated photons, ready for use in quantum communications. The difference from classical systems is extreme miniaturization. Millimeter-sized devices can replace equipment that previously took up entire tables. Their integration into CMOS platforms opens up a future where quantum chips are manufactured on the same lines that produce conventional microprocessors. This lowers costs, facilitates scalability, and allows us to think about quantum networks being deployed at the same rate that fiber networks are expanding today. Entanglement is no longer a delicate experiment, but an industrializable product. Recent advances show that the quality of the pairs generated rivals that of the best traditional optical sources. Current challenges focus on improving spectral purity and reducing losses in coupling with external fibers. Every thousandth of a decibel counts in preserving state fidelity. Taken together, these micro-resonators are one of the clearest promises of quantum democratization. When they can be mass-produced, entanglement will travel through the global infrastructure as naturally as classic internet signals do today. 68. The link between entanglement and the emergence of consciousness. Beyond the neurological, some philosophers and physicists speculate on the possibility that consciousness itself is an emergent phenomenon related to quantum correlation patterns. This is not a proven claim, but rather an attempt to explain how subjective experience could arise from material systems. Entanglement, by creating a whole greater than the sum of its parts, offers a powerful analogy for describing the unity of conscious experience. This idea has generated passionate debate because it touches on the boundary between science and philosophy. For some, it is a mistake to mix the quantum with the mental without solid evidence. For others, it is a legitimate line of exploration that could provide a formal framework for age-old questions. In any case, the discussion enriches the dialogue between disciplines and avoids easy reductionism. There have been experimental attempts to study whether patterns of collective coherence in neural systems could correlate with specific mental states. The results are ambiguous, but they serve as a starting point for more rigorous methodologies in the future. Even if the hypothesis proves false, the data collected could shed light on how biology organizes information at levels never before explored. The relevance of this debate lies not only in what it says about the brain, but in what it reveals about us as a species. The simple act of asking ourselves whether consciousness could be interconnected forces us to broaden the way we think about the mind, reality, and our own identity. 69. Entanglement signatures in solar plasma. The sun is not just a ball of burning gas. It is a natural laboratory of extreme physics, where magnetic fields, charged particles, and radiation interact in chaotic ways. Some models suggest that certain quantum coherence phenomena could play a role in plasma dynamics, especially in how energy is distributed on microscopic scales. Detecting traces of entanglement in this context is a formidable challenge, but not impossible. Collective oscillations and correlations in radiation emission could contain statistical signatures that cannot be explained by classical plasma models. High-resolution instruments in solar orbit could, in theory, reveal patterns that betray collective quantum dynamics. Even without direct confirmation, the hypothesis has spurred new lines of research in quantum astrophysics. The importance is twofold. On the one hand, a better understanding of the physics of the sun is essential for predicting solar storms that affect satellites, power grids, and communications. On the other hand, detecting quantum correlations in such a huge system would prove that entanglement is not fragile or limited, but can survive in environments of extreme heat and turbulence. Every piece of data collected from the sun, from its spots to its emissions, could be hiding a deeper code. If we learn to read it, we will not only understand our star, but we will also have clues about how matter works under extreme conditions throughout the cosmos. 70. The horizon of quantum applications in everyday life. Looking to the near future, entanglement will cease to be a concept reserved for physicists and become part of everyday life. It will materialize in secure ATMs, immediate medical diagnoses, clocks that never lose sync, and transportation systems that navigate without the need for satellites. The promise is not that we will understand the equations behind it, but that we will use the fruits of those equations without noticing. The first phases are already underway. Banks testing quantum cryptography, cities installing fiber links for pilot networks, and companies developing quantum sensors for resource exploration. In a few years, integration will be so natural that no one will remember a world without these layers of security and precision. Just as we rely on GPS or the internet today without knowing how they work, tomorrow we will rely on entanglement. The key to this leap will be miniaturization and standardization, processes that have already occurred in previous technologies. What began as laboratories full of mirrors will end up as chips encapsulated in domestic devices. That change will mark the true triumph of entanglement, ceasing to be a mystery and becoming an invisible tool that improves our lives. When quantum physics becomes commonplace, our relationship with reality will have changed forever. We will live in a world where paradoxes have become infrastructure, and where yesterday's impossible will be tomorrow's silent standard. Quantum entanglement has led us to understand that reality is not rigid or static, but a living fabric of invisible connections that traverse the entire universe. Each discovery opens up more questions than it answers and reminds us that what we call reality could be much stranger than we imagine. And if this topic has fascinated you, the journey does not end here. At the end of the video, you'll find the wave-particle dilemma. What does the quantum world tell us? An even deeper enigma that will change the way you see the world. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be stranger than we believe. Science is the most powerful way to understand this strangeness.